Okay, the Green's theorem, we start what is called the integral theorems of multivariable calculus. I am not going to do a proof here, we are not going to prove Green's theorem. The proof would take half an hour. So, maybe Green's theorem proof I will put it in put up in the portal, but maybe I will try to do a proof of Stokes theorem or in Gauss divergence theorem if time permits. So, what is Green's theorem? Green's theorem actually relates a line integral with a surface integral. That is what Green's theorem does. And we have so suppose I consider in the a vector function from R2 to R2 given as then given a, so here the line integral is a special form of a line integral. So, suppose we are looking at a region bounded by a curve. So, this is a domain D which is bounded by a curve C, and I will always evaluate the line integral along the curve C if I move in a direction which I will call the positive orientation, in the sense that if when I will move along this curve, the area of this domain should always be on my left hand. That is the criteria that I will follow. So, if I am moving along this curve, so if I am moving counterclockwise along this curve, then the area, if I am this guy here, then my area is always on the domain's area is on the left hand. So, Green's theorem states the following fact, that for such a kind of domain, we will get into more details. So, this C, this curve C is the boundary of the domain D. So, they write this as del D. So, I will follow the book's approach. So, it is del D P dx plus Q dy. This is same as integral over surface integral over the domain D del Q del x minus del P del y dx dy. Q is associated with y. So, when you differentiate it here, it is with respect to x, and P is associated with x when you differentiate it here with respect to y. So, this is the thing that you have to remember. So, how do I decide which direction is my positive orientation? In these kind of curves, you see, if I'll take the, so this is my domain, the domain. So, this is outside the domain. So, this is any vector v from a given point pointing perpendicularly, normal. If I draw a kind of tangent line here, there is a normal which I call the v out vector, means is pointing toward the outside. Now, if I am in 2-dimensional space, so if this is my k vector, right, which is pointing. So, this is my 2-dimensional space in which I am lying, and k vector is pointing in the perpendicular direction. So, the vector, this vector is k cross V out. That vector, that direction is the direction of positive orientation. So, if you look at that direction, you immediately understand that if I walk down, then my domain has to always remain on the left hand side. So, the Green's theorem always expects del D to be covered or oriented, to be oriented in the positive direction, in the positive sense, means if I move around, that would be the way I will move around. So, I am writing in green because it is Green's theorem. Green's theorem actually arose because of some computations with electrical potentials and gravitational potentials. Stokes' theorem was actually told to Stokes in a private letter, as the book says. I have to check out the history a bit more, by Lord Kelvin, famous for its absolute temperature, absolute 0. So, the Kelvin scale. So, and Stokes gave this problem in a math examination in 1854, which, and gradually it became famous as Stokes' theorem. Now, so you see here there is a link. Now, how do you know that this is a line integral? So, if I have written f like this, so you know here I can take the r curve and then you put r plus dr. So, this is your ds. So, ds is measuring, the ds here is almost same as dr, very small, because dr is very small. So, we can write this as dx I vector plus dy j vector, and that is exactly the way you compute ds. ds square is root of dx square plus dy square root over dx square plus dy square, you know this already. So, here if I do my f dot ds, and this is nothing but p of I vector, I am not writing x y, and q of j vector. Sorry, not p, sorry, making a mistake, p of dx plus q of dy. So, this will give me a scalar. So, this is what it is. So, if I write integral, so if I write integral del d f dot ds, that is same as writing integral del d p dx plus q dy. So, if it is difficult to compute this, you just compute the surface integral. That's the message of Green's theorem. Of course, there is another requirement, P and Q. So, these are the assumptions under which Green's theorem is true. P and Q must be continuously differentiable. Of course, we need continuity here for the integration to go through smoothly. Here all integrals are meant, when you take the single integrals, they are meant in the Riemann sense, or most cases it is in the standard Newtonian sense. That's the really the effective thing. That's, now let us start giving one or two examples and see how we can understand. So, we will take examples from the book and one by one we will try to work them out. So, here is a problem that says, okay, you take a curve which is lying along the boundary of this square formed by 0 1 0 1, that is the domain D is formed by 0 1 cross 0 1. So, it is 1 0 0 0 0 1 1 1. Now, I have to traverse in this direction. You see I have to traverse in, so this is my C which is del D. So, this is the direction I should be traversing along, the four sides. So, when I am traversing along means I am starting from one point and coming back to the same point, that is the meaning of del D, that you take a complete round of the boundary. So, you start from one point and come back to that point, that is the meaning of del D. So, they are asking you, can you integrate on this del D boundary of this particular domain integral y4 plus x cube dx plus 2x6 dy. So, here is my P, here is my Q, but I go from one point and come back to another point. So, you might feel that I have gone from the same point to the same point. So, it is a kind of very strange. So, how will I actually, I made a full circle, it is not going from A to B, and so I have separately I can work them out. I will work out what are the limits of those 2 points or limits of the t, the parameter, and then I will work it out. So, here if I want to talk about such kind of line integrals, then the best way is to use the Green's theorem. So, in this case I will now write integral d. So, it is del q del x here. So, what I am going to have here is del q del x minus del p del y dx dy. So, what is my del q del x? Is 12 x 5 minus del p del y, that is 4 y cube, do del x del y. So, here x is varying from 0 to 1, y is varying from 0 to 1. So, that makes life much more simpler. Okay. I will not write down the answer here, I will just write down the answer, here it is 1. So, Green's theorem allows you to calculate this line integral and gives you 1, which is not so easy. If I give you a complete circular path, if you go and look at the line integrals chapter where you have studied line integrals for the first time, see all the paths are usually open paths. Especially if you have a how do you compute a total path? So, you go by one path. So, you go from A to B by one path. So, when you compute this, if you have to compute the line integral here, first you compute on this path, then you compute on this path, then you compute on the third path, then the fourth path. So, you start from 0 0, compute up to 1 0. Then you start from 1 0, compute up to 1 1, then you from 1 1 you compute up to 0 1, then 0 1 to 0 0. That is the 4 different line integrals you need to calculate if you want to evaluate the line integral that we are choosing. But just by applying Green's theorem, just by applying Green's theorem here, you have just solved the thing in one shot, and that is the applicability. A very interesting application of Green's theorem is the area. So, if let me tell you that before I get into this area business, let me tell you that there can be regions which are much more complicated than the simple region that we have drawn there. There can be a region like this with holes inside. Now, here what you mean by positive orientation? See, positive orientation would always mean, here when you are encircling the region, you have to go, so the region is actually here, this is the domain. So, these are holes, so this is a C1, this is C2 and C3, that C1, C2, C3, all three together make up the boundary. So, in such cases how will you do? These are the cases where this Green's theorem becomes useful, you do not have to bother too much about it. See, here along C1 I move in the counterclockwise direction, but along C2 I have to move in the clockwise direction, and C3 I have to move in the clockwise direction, because my positive orientation has to follow one very simple thumb rule, that my area, the domain has to always remain on the left side as I work on that curve. So, here on the internal curves you have to go on the clockwise direction, on the external curve you have to go on the counterclockwise direction. That is something you have to keep in mind. And now area, so suppose you have a kind of closed curve C covering a domain D, and the area A can be computed by this simple line integral. And how do we know that area can be computed by this simple line integral? Because suppose now we construct a vector field F, where it is minus y I vector and x j vector. So, let me look at this integral, half of integral C minus y dx plus x dy. So, this is your P and x is your Q. So, this is my P and this is my Q. So, this is your f dot ds, and then I will integrate by Green's theorem, I will integrate over the domain D, and Green's theorem should give me del q del x minus del p del y. So, what is del q del x? It is 1. Half of, so here a line integral is computed just in one shot through a double integral. So, what is del q del x here? It is 1 minus del p del y is minus 1. So, minus of minus 1. So, this is, so I will get half of, this is not infinity, this is the domain D. So, half of integral domain D 2 of dx dy, and that is equal to integral D of the domain dx dy, and that is exactly the definition of the area. That is the magnitude of the area. So, you see how beautifully this has worked, how beautifully this has. Now, there is another interesting way of expressing the, I am not giving the proof I will send across, expressing the Green's theorem, which is called the vector form of the Green's theorem. That is what we are going to now learn. Vector form So, again the same story. So, you have f vector given as p I vector and q j vector. I am not writing the x y's. So, what does it here? They say that you can write this line integral as integral curl f, means curl has a sign, this is a curl sign, curl f has this sign, curl of f. So, let me just remind you, this is the sign we will use for curl f. Curl of f dot product with k vector dx dy. This is what as another form is called the vector form of Green's theorem. The other form was written in the form of a scalar. So, we have to see whether this vector form has some meaning or not. So, let us see how do I prove it. So, f is p plus p I plus q j. Now, curl is in terms of 3. So, basically you are here I have to write it in 3 components 0 k. So, curl of f is by I j k del x del y del z p q 0. So, it is I vector into this part which is 0 minus del q del z minus j vector which is 0 minus del p del z, and this del q del z is 0 and del p del z is 0, k vector into del q del x minus del p del y. Now, you see this is completely 0 because there is no z in q, it is in terms of x y. So, basically this is 0, this thing is 0 and this thing is 0 because p is a function of x y only, not x y z. So, I am writing everything stepwise. So, I wrote this. So, it is what we have here is nothing k dot del q del x minus del p del y. And what do I have here? So, I have here f vector. If I take a dot with k vector, I will simply have this as del q del x minus del p del y, and this simply gives me back the form in which I know about Green's theorem. So, this is another way to integrate the curl of f dot k. This curl of f will become important when we will be talking about Stokes' theorem, right. So, there is a kind of result where we will not talk much about it. It is called the Gauss divergence theorem in the plane, because Gauss's integral, Gauss divergence theorem relates the integral of the divergence of a function, the line integral basically, surface integral. The surface integral of a divergence of a function over a given surface is related to the volume integral over the volume, or the triple integral. The volume integral is a triple integral with respect to the volume enclosed by the surface. So, that is how Gauss is, what is Gauss divergence theorem, and that is very important in electrostatics, is also important in mechanics. So, of course, in fluid mechanics naturally. So, fluid and classical both. So, there is something called Gauss divergence theorem on the plane. So, I will just make a statement of this and end the talk here. Gauss divergence theorem on the plane. So, it says that this line integral, here S is not a surface, but a small arc length. The is a surface integral in terms of the divergence of f. The proof here is slightly not simple. I would not like to give the proof here at all. So, it needs some more ideas from vector calculus which will confuse you. So, we will not go to all these things. So, there are several, for example, just as an example, I will end before I end the talk. For example, there is a problem here, evaluate integral c y dx minus x dy. Do not immediately jump to the conclusion that this is some kind of area, because look at the area. Look at the area stuff here. Area is x dy minus y dx. Here it is y dx minus x dy. It is kind of negative of area, right. So, here you have the domain D as minus 1 cross minus 1. And your C is the boundary of the domain, oriented in the positive sense. How will you evaluate it? There is one simple thing to observe. First, observe that I can write this, let me write down that this integral can be written as minus integral of x dy minus y dx over this C. So, what is area? X dy minus y dx. So, x dy minus y dx is area, in fact twice the area. So, this is minus twice the area. So, what is the area here of this domain? One side is 2, another side is 2, it is 4. So, minus 2 into 4 is minus 8. But if I go in the clockwise direction, the opposite direction, because this would be, if I go in the clockwise direction, the value of the integral would have a negative sign here. So, it will become 8. So, the problem says here to go in the clockwise direction, but let me just keep it in the anti-clockwise direction, we go, and so the area of here, this is nothing but minus or twice the area, and this is minus 8, that is the answer. So, that is how you apply what you have learnt here. So, with this I end my talk here, and let me tell you, 7th week is finished. There are 4 lectures in 7th week, because the 2 lectures on surface integral has been combined into a single lecture, which you know is pretty involved. Green's theorem, once you know the formula, the statement of the theorem, you know how to apply it. and that is what we will concentrate on. That is what we, and proof of Green's theorem will come later as a part in the portal. It's not a part of the whole thing. Let me see what I can do if I can give a problem, if the proof of Stokes theorem can be done in the class, but I do not think it can be done in the class. Maybe I will just for kind of a mathematical work to be done, so that you do some math and think about how proofs are done here. Maybe I will try to do the Stokes theorem here in the class, but Gauss divergence theorem I do not know how much I will have time to do, but we will do something about it. So, let me tell you here, the exact divisions may not be maintained. So, we will cover Stokes theorem, its applications, Gauss divergence application, and we will speak about fields in the 8th week, because fields has lot of link, and how differentiation and integration is linked here in this vector situation, and how these ideas of curl, gradient, divergence can be applied to several physical situations, those things will be discussed. So, overall I have to provide you a content of 2 hours and 30 minutes. So, I will try my best to cover the thing in 3 hours, which could be in a talk of 4, which could be in a talk of 1, 2, maybe 4 and 5. So, it could be in a talk of 4 or 5. So, but the 7th week also ends with 4 talks, because 2 talks have been combined in one, the surface integral. The idea is that why I combined them was because if I just separate them out, then it loses the link. So, I cannot talk about line integrals and suddenly I do not speak about orientation, because that is how the idea of I do not speak about surface integrals and I do not speak about oriented surfaces, because otherwise the parallel that you have learnt in case of line integrals would become lost. So, that is why this, or if I divide this thing into 2 parts, a little bit thing for one lecture, then another lecture little bit thing, then the link gets disturbed. So, it is better to go in one flow. So, 2 talks have been jammed into one. So, there will be 4 talks, one having almost an hour. So, thank you very much, thank you for being patient, and we are ending the course, and hope the journey was fine, and hope many of you would find something useful from this course to take. Anyway, with the YouTube is with you, and so you can always go back and forth, and you can always write on the portal anything that you want to discuss with us. Thank you.